All right, so exercise 2 gives us an example of the inverse version of this. So let's just read through the questions down. We have birth weights are normally distributed. Like I said, you'll always have this keyword letting you know we're doing something with the normal curve, with a mean of 109 ounces and a standard deviation of 13 ounces. Answer the following questions using this information. So we already know whatever we're doing, we can draw a beautiful curve centered at 109. And then reading through the first question, it says a hospital puts an infant in the lightest 2% in the NICU and asks what is the cutoff for putting a baby in the NICU. So the easiest thing to me is to spot here that we've been given a percentage, which means we don't have the actual cutoff itself. And then they asked us for a value. So first thing I have to decide is where we should be shading that 2%. Lightest would be on the left, so this baby would not weigh very much. And then we have two ways we could handle this. One, we could do it by hand. If we're doing this by hand, we're going to use the percent to find a z-score. So you can either search the middle of the table for 0.02 or do inverse norm, whatever it might be. So I'll pretend that I don't have the calculator, and I'll do this with a table. So I'd search the middle of the table for that 0.02 because that's a left side probability. So 0.02. This looks like it's the closest, barely. It's 2 10,000ths away versus 3 10,000ths away. So the z-score would be a negative 2.05, which makes sense. We need a z-score that is pretty far away. It's pretty unusual and is negative because it's small. And then your step 2 would be to calculate this. Last piece would be take that z and turn it into an x. Now you could use the z-score formula, but easier than that, I give you a formula sheet on the test. And if you see here, we actually have the inverse. So this is basically solved out for x. So you should use that formula. X is equal to z times sigma plus mu. X is equal to z times sigma. Basically, how many bunny hops am I away from my mean? So negative 2.05 times our standard deviation plus 109. Times 13 plus 109. We have 82.35. Very important because I will dock points on both the worksheet and on a test. You definitely need units here. So everything was in ounces. So we're talking about a birth weight for a child in ounces. So that's what you need there. And now, of course, I'm not going to do this by hand ever again. I would instead be using inverse norm, which remember you feed the left side probability, so 0.02, then your mean, and your standard deviation. So if we do all of that, go into my distribution menu, grabbing inverse norm, and we're just going to type in all of our information. Now this might end up slightly different. It's not going to have the same level of accuracy as our normal CDF versus our table, and that's because we're going to take something that was a little bit off and multiply it by a number, make it even kind of more off. So you might have a bit more difference here. So you can see we have 82.30 ounces versus 82.35 ounces. So, like I said, the calculator is way more exact than the table just by the nature of the fact that we don't have rounding on our z-scores. So I would recommend take time to set up the rest of these. I'm going to brush through them and give you the inverse norm, but it's worth trying them on your own before you watch me do them. So, 95th percentile. 95th percentile means that this baby is heavier than 95%. Percentiles are one of the easier things to deal with because they're just giving you a left side percent. So inverse norm, 0.95, 109, 13, which gives us 130.38 ounces. All right, heaviest 10%. Whoop. Now we have a keyword that lets us know that that 10% is on the right side, right? Heaviest. And if we just think about it sort of with common sense, we're going, okay, heaviest 10% of babies, that would be a baby that's above average. So now our cutoff that we're looking for is still on the right side, but they've given us 10% as a right side probability or right side area. So we're going to have to, before we go to inverse norm, figure out the left side. Figure out that baby is then heavier than 90% of babies. So inverse norm needs 0.9, and then you're 109 and you're 13. Now if you do this incorrectly and you plugged in 10%, as long as you have your drawing, you will have a quick, it'll just immediately tell you you're wrong because you're going to give out a value that is less than 109, which doesn't make sense with your drawing. If we do it this way, 125.66 does make sense in terms of falling above 109 and being a pretty heavy baby based on our bunny hops, our standard deviations. We have the middle 80%, just to remind us about those middle questions. There is one on the worksheet. So again, we're having 109. Middle means that our shading would start in the middle of the distribution, and we're shading about 80% of the curve. So we're shading a good amount of this curve, right? Almost everything. It's not looking symmetric, but bear with me. And we're going to have two different cutoffs. And even says, what must it weigh between? So we're going to get two different values. So we'll call this x1, since we're not looking for z's, and this one x2. x1 will be inverse norm. If 80% is in the middle, that means you have 20% left over or 10% on either side. So the first one will be inverse norm of 0.1, still with our mean and standard deviation. The second one will be inverse norm of 0.9, still with that mean and standard deviation. End up saying that a normal baby, and sometimes it helps to actually write this out as a sentence to just sort of double check, will weigh between 92.34 and 125.66 ounces. Now, just be aware you don't need to subtract these. I always get students who want to go a little bit too far and do a subtraction to find that range. We actually want those two cutoffs. The last one asks us for Q3, which is a way to say the third quartile, which is another way to say the 75th percentile. So this is just a fancy pants way for me to say percentile again, bringing us back to our knowledge of part 2. So still at 109, but now we want the 75th percentile. So whatever this is, we want the area to the left to be 75%, which is the perfect setup for inverse norm, right? Inverse norm wants a left side percentage. So I won't even figure out what that is, but you get the idea, hopefully. That's basically every possible way I can ask this question. I can give you a left side, a right side, or a middle, and then you have to find those different cutoffs using inverse norm.